Okay, so now you recall, here are some common rules that you already have learned for doing derivatives of certain functions. Now remember, of course, that the real derivative, the master rule, is the limit as h goes to 0 of the difference quotient. That's the definition of the derivative, and it's the rule that works for all kinds of functions. Of course, you have to be clever enough to get rid of that h in the denominator and figure out some way to do that to show that that limit exists. But I always just am preaching that that's the real derivative. That's the rule that applies to all functions. Then we know some nice rules of thumb for certain functions. Like, for instance, we know the derivative of the cosine function is negative the sine function, and the derivative of the sine function is the cosine function. Look how beautiful this is. These are kind of locked in this little loop. You take the derivative of one and you get back the negative of the other or the other one. It's really beautiful. So it's really cool because cosine and sine are periodic functions, and their derivatives are also related in this sort of cyclic kind of loop. It's really, really cool, in my opinion. Okay. Other cool derivatives, of course, are things like, you know, the derivative of the exponential function, e to the x. Remember, that is, when you look at a to the x, this is an exponential function with base a. A is some number in this case. When we let a equals e, when we let it equal e, the 2.718 dot, 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 this is this incredibly important constant. It's just as important and famous as pi. Such a big deal in math, e. In any event, when you let that be the base of your exponential function, you model all sorts of phenomena in nature and in the sciences and in mathematics. The exponential function is what we call e to the x, the exponential function. If somebody comes up to you and they're like, hey, let's talk about the exponential function, you're not going to be like, which base do you mean? 10, 2? Which base do you mean? No, that's an exponential function. The exponential function always means the case e to the x. And it has the super badass property that when you take its derivative, you get back the function itself. Now that's really remarkable. Kind of like with sine and cosine, these are periodic, kind of cyclic kinds of functions, and they get locked into the cyclic loop with their derivatives. Here, the exponential function is this really natural function that models exponential growth and decay. And when you take its derivative, that naturalness of the function comes back and returns as the derivative. Just like the cyclicness of these functions kind of get reflected in their derivatives. That's very cool. Hold on just a second. I'm getting weird lighting from this angle. Okay. All right. So now, of course, the most famous rules about derivatives, these are really like the things that most people even think about being derivatives when you're in high school or when you just know a little bit of calculus. Of course, you know, the power rule. And the power rule just says that if you take the derivative of x to the a, or whatever variable you're differentiating with respect to, you know, of course, that the constant a comes down in front as a multiplier, and then you get x to the a minus 1. It drops down. Cool? So for instance, if a equals, let's go like say a equals 3, well, then the derivative of x cubed is 3x squared. Notice this is a quadratic. A quadratic is a squared, a polynomial where the highest power is 2. It's a quadratic polynomial with just one term. But the point is that if you take the derivative of something to the third power, you get back something to the second power, all right? If you take the derivative of something to the second power, of course, you get back something to the first power, a linear function. If you take the derivative of something to the first power, well, of course, the derivative of x is 1. The 1 comes down, the power drops down to 0, and you get 1 times x to the 0. What I'm trying to point out here is this. Notice the pattern here. You take a derivative, and you get back something that looks similar. It's another power function, but it's dropped down by 1 power, by one in the exponent. Cool? It's a nice pattern. You take a derivative of something to a power, you get back something to a different power, and it's dropped down by 1. So you're able to produce by derivatives all of these powers, right? If you want to get something to the times x, you're going to be, as a derivative, you're going to be taking the derivative of something times x squared. So that when you take the derivative, the power drops down to an x. If you want to get something as a derivative, a function, if you want to find a function as the derivative of some other function, that's a squared, like x squared, a quadratic, well, you're going to be taking the derivative of something cubed, and so on. If you want to produce a function to a certain power, a power function with a certain exponent, then you need to take the derivative of the next power up, right? This is kind of like the opposite way of looking at the power rule. The power rule is saying you can get all of these things, anything that looks like this, x to the something power, you can get that by taking the derivative of the next step up power function. And it works all the way down to here, to x to the 0. Well, what about negative powers? Can you get the derivatives of negative powers? Yeah, sure. Right? Because, for instance, let's say that you take the derivative of 1 over x, which is just the derivative of x to the minus 1 power. By the power rule, the negative sign comes in front. You subtract 1 from the power, and you get negative x to the minus 2. So you can get x to the negative 2 by taking the derivative of something x to the negative 1. And similarly, if you take the derivative of 1 over x squared, or something x to the minus 2 power, of course, you're going to get minus 2 x to the minus 3 power, and so on. The point I'm trying to say is that the same pattern still holds for negative powers. You can get any negative power by taking the derivative of a power function that's 1 step up, right? Like if I'm like, what would you need to take the derivative of to get something times x to the negative 7th power? You're going to be like, oh, you need to take the derivative of something times x to the negative 6th power. The power rule will make it drop down 1, and you'll get something times x to the negative 7th power, right? I'm just saying, for every x to the a, you can find x to the a times some constant, usually times some constant. We're just going to let this be any constant for now. You can find that this is going to be the derivative of some other constant. I don't know, we'll call it C2 times x to the a plus 1. I'm just saying, this is like what the power rule looks like. Anytime you want to get x to some power, you can get it by taking the derivative of x to the next power up for all powers. Well, is that true for all powers? Let's think about it again. If we want to get, well, certainly if we want to get x to the 0 times some constant, we can get that by taking the derivative of some other constant. We'll call it C2 times x to the 1, right? The 1 power comes down in front, it drops down. In this case, the constants are the same. If you want to get something times x to the 1 power, well, you're going to take the derivative of something times x squared the power comes down, it drops down by 1, and you're going to get a linear. I'm just rewriting the same thing I wrote before, and so on. Some other function. These C2s and C's aren't all the same. This is just very general. I'm saying if you want something of this form, you take the derivative of something of this form, right? Okay, totally good. We all get this, okay? Same thing works if we go in the negative direction. Totally fine. For instance, if we want something of the shape C times x to the minus 2, like I just said, we're going to look at something like this. The derivative of C of some constant times something x to the minus 1, right? Again, minus 1 comes down, it drops down by 1, and you get to the minus 2 power. Same thing for minus 3, some other constant times x to the minus 2, right? This is just same thing, keeps going by the power rule. The power rule allows you to catch all of the power functions as derivatives of other functions. Or does it? How does the power rule give us C times x to the minus 1 as a derivative? How does the power rule give us that power? Obviously, it doesn't. We listed all of the powers. Let's just go down again. If you want to take the derivative of x to the 1 power, well, you're going to get x to the 0 power. If you take the derivative of x to the 0 power, that's just 1. Well, that's 0. That's 0. That's not x to the something power. That thing turns to 0, and there's like a wall there. So if you want to go down to the negative derivatives, well, the derivative of what is going to equal something times x to the minus 1. The power rule doesn't give us any function that does that. The first function that steps in that it works would be x to the minus 2. Sorry, if we take the derivative of x to the minus 1, well, then we would get something to the negative 2 power. And from there on down, we're good. But there's a hole right here in this list where we don't have a derivative that gives us something of the form x to the minus 1 times a constant. We don't have that. Do you buy that? This list of power functions doesn't include any function that gives you something to the 1 over x. That function comes by squeezing another function in between the power functions. It turns out, remembering that the derivative has to do with the rate of growth, okay? So the rate of growth of x to the 1 power is 1. The rate of growth of x to the 0 power is 0, all right? And the rate of growth of x to the minus 1 power is minus x squared. This function that we're looking for that needs to fit right here to give us something sorry, that's x to the minus 2. So sorry about that, x to the minus 2. The function that needs to fit right here to give us something that gives us x to the minus 1 power has to be something that has a rate of growth in between these. Well, in fact, hold on a second. This is supposed to be minus. This is a positive number, 0, negative number. And so, oh, wait, hang on. Sorry. This is a positive number. What we're going to be looking for actually doesn't quite fit right there where I had claimed it would. What we're going to be looking for is a function that fits here. Some function that grows a little bit faster than 0, that's flat, right? The slope is flat. And a little slower than having a slope of 1. Slope m equals 1. It turns out that the function that fits into the power rule in this way is not a power function, but it's the natural logarithm function. The derivative of the natural logarithm function is 1 over x. also known as x to the minus 1. So in fact, to get a function that will give us -1 as a power in this chain, we need to reach the logarithm function. And what this tells us is that the natural logarithm function grows a little faster than a constant, 1, x to the 0, but it grows slower than x. So it's kind of wedged in between there. And so in this kind of ladder of power functions and their derivatives, we can still get x to the minus 1 as a derivative. We just have to take the derivative of the logarithm function, which is very impressive about the logarithm function. This is really powerful because, as you might remember, the logarithm function has a lot of nice properties. Well, first of all, natural log of x is the inverse function of e to the x, which is to say, if you take e to the x, e to the something, and you plug in the natural log of x, they cancel, so to speak, in a function theoretic way, and just give you back x. If you plug a function inside its inverse function, you get back x. And the same goes if you take the natural log of e to the x. The natural log and the e cancel, so to speak. That's what it feels like. And you just get x back. So this is like kind of the definition of the natural log. Of course, in pre-calculus, we use logarithms in some really tricky ways. There's a whole arithmetic of logarithms that's very beautiful. And I can't go into all of that now, but I encourage you to review it just really because it's like some of the coolest stuff in all of mathematics. It's incredibly useful, and we're going to be using it in this unit. But here are the basic laws of logarithms, and I just want to remind you of them, besides the couple of properties I just gave you, which are pretty fundamental. Well, we have that. I'm going to give you these rules for the natural logarithm, which is the logarithm base e, for those of you who are wondering, where e, of course, is the magic number that I mentioned before, 2.718 ... Okay, so the natural log of x is, by definition, the log base e of x. I'm just telling you, reminding you. And all logarithms, including the natural log, share these properties. I'm going to write them for the natural log, but they work for all logarithms. Well, they have a special property that the logarithm of a product, say the logarithm of a times b, is equal to the natural log of a plus the natural log of b. Logarithms take a product and split them up into a sum of two things that are easier. This is a smaller number, each of these, than this. This is easier to compute by hand. And in any event, this might be really complicated. But you can use logarithms to break the problem up into simpler pieces that are individually easier usually to use. Notice A and B don't have to be numbers in this case. They could be functions. And that's going to be really useful in the coming week. That's why I'm reminding you of all of these. Of course, another rule is that if you take the quotient of two numbers or functions, the logarithm breaks that quotient up into simpler pieces as well. It turns it into a subtraction problem. So logarithms turn multiplication inside the logarithm into a simpler sum. It turns multiplication into addition. And it turns division into a simpler difference or subtraction problem. And logarithms have another really amazing property. This property is probably the most useful for this class, which is that the logarithm of some number or function to a power of another number or function. Well, logarithms take powers like this outside of the logarithm and in front, like as a multiplier. So we actually get this power b from inside the log. It comes outside as a multiplier. Then we just get b times the natural log of a. Notice if this is like 5 to the 100th power, that's a that's a really big number. But 100 times the natural log of 5, that's totally reasonable for you to compute. You could do that by hand, just by shifting the decimal places. So I'm saying like huge number, really much easier number. And these all go backwards as well. These rules don't just go left to right. If you see something in this form, you can take the multiplier inside as a power. And so, of course, we have things like, here are a few special cases of using some of these log rules. So for instance, the natural log of the square root of x, I'm going to go ahead and put parentheses there. Well, that's the natural log of x to the 1/2 power. We're rewriting the root in a way that's more useful using the theory of exponents. And then using the property of logarithms, that 1/2 can come in front as a multiplier. And we get 1/2 times the natural log of x. That's a much simpler function. You know what the graph is probably just by memory. A natural log of the square root of x, I'm not quite sure what that looks like off the top of my head. So this is simpler. Okay, and let's see, for instance, a couple of other things. The natural log of e is the log base e of e. That's like the definition. E to what power equals e? Well, of course, natural log of e is 1. And that goes for the log in any base of the base. And we have that the natural log of 1, e to what power equals 1? Well, it's 0. I'd say that these are the two most important properties of logarithms, along with the natural log of a to the b, or let's say x to the b, is equal to b times the natural log of x. I think I messed up when I wrote that before on the previous slide. When I think I had a to the b and I put x over here. So please excuse that typo retroactively. I mean, like, that's the beginning of the story of logarithms, these nice rules. It's not the end of the story. But what I want to note is that these rules introduce into math a whole new set of arithmetic things that you can do that you couldn't do before. You don't have things in math, in arithmetic, where you can turn products into sums and quotients into subtraction, and where you can just pull exponents in front. Well, you can do it with differentiation, but that's not arithmetic, that's calculus. So in any event, using logarithms are really useful for a large number of reasons, and they're really beautiful for a number of reasons in math. But in particular, logarithms allow us to use, they give us some new extra rules of arithmetic, the ones I just went over, to help us solve and simplify our math problems. There's a lot of really cool and impressive things about logarithms. They're extremely beautiful. But as far as this class is concerned, logarithms give us these new, really pretty sick rules that we just went over. And we're going to use those in more complicated situations than you did in pre-calculus in order to leverage logarithms to find derivatives of more complicated functions. And that is coming up in the next week.